So thank you very much, and thank you very much to organizers for the invitation. And maybe it's a good time to say thanks to the organizers, so I will propose a small applause. Yes, I really have learned a lot. So I will talk about limit theorems in finite free probability. So I will talk about joint works with Daniel Perales, Jorge Garza Vargas, Sam Johnston, Yuki Ueda, Katsunori Fuji, and Josue Vasquez Becerras. So they are all very young. I'm very glad to have worked with them, and that they think that problems we discuss are interesting. I will also talk about, of course, works of Marcus Spielmann and Sirivastava, and of course, and by talks of works of Kablushko, Hoskins, and Steinerberger. But I will say that there is other very interesting works which I won't be able to talk about by Andrew Campbell, Jacob Campbell, Shane O'Rourke, David Renfrew, Brian Hall, Qingwei Ho, and Jonas Jalloway. So I also motivate to see these papers. They are also very interesting, which are related to this talk. Okay, so I will talk first about finite free probability in general, then about finite free cumulants, and then about some limit theorems about finite free convolution, and maybe at the end, if I have time, I will talk about two things which are related to finite free convolution, which are maybe in a different perspective, which were really unexpected at the beginning. Okay, so what is finite free convolutions? So the usual perspective is from asymptotic freeness is given by you take two random matrices A and B, or maybe two matrices, two sequences of deterministic matrices, and you rotate one, and then you look at the trace or the expected trace, which we call the moments, and we associate a measure which has these moments, and then look at the n going to infinity. And so the new approach is, or the new perspective is, instead of looking at the expected trace, you look at other quantities, which are the expected characteristic polynomial. And so this is a different operation. And what is nice is that actually this is also related to free probability. And so this was, so let me just be more precise. So you consider A and B, and you take the expected characteristic polynomial of A, Q, B, Q transpose. So here I choose orthogonal matrices. You can, as it was mentioned before, you can take unitary sign permutations and other groups, and they all give the same. And what is non-trivial and very interesting is actually that this is an operation which preserves real rootness, meaning if I have P and Q, which are real root, then have real roots, then also this operation is real rooted. And of course, this doesn't depend on A and B. Good. And actually, there is a precise formula for this. So the polynomial that you get is exactly this. So basically, you multiply the coefficients, and then so you do convolution of the coefficients, and then you multiply by some coefficients. And actually, you can formulate this as a classical convolution if this was done. This is well understood that you can relate this to classical convolution by thinking of A's and as expected moments. Okay, so this is one perspective that I won't talk about, but you can do this. So if you think this as a convolution, this is correct. Okay, and this was a theorem made from more than 100 years ago that this is real rooted. And you can do the same story for the product.
Can I probably ask you already? Is there a simple proof of this? Maybe by now I keep asking that.
What?
That P plus Q is real rooted. Is there any simple proof of that?
I don't know. I don't think so. I don't think like real simple. Like if you can
like something
to high school. No.
That you could explain in 3 minutes. Nothing
I don't know. Probably not. Maybe Nikhil knows, but.
You can explain it in 10 minutes.
Okay. Yes. And this is the same story. You take the product of two matrices, and then actually the convolution is even simpler. You just take products of of your coefficients, so 1 by 1, and you normalize correctly. And again, you can think this as expected moments of a product of two random variables. Okay, and the real rootness was proved by Sego 100 years ago. Okay, so in the original paper of Markus Spielmann and Sylvia, they were more interested in this kind of inequalities. Basically, this says that the R transform is smaller than the R transform of the free convolution, and a similar thing is done for the S transform. Maybe I need to put some tildes on the right, but okay. And this was translated into, the alpha max roots, and this was important for them because they could use this to prove these very nice theorems about Ramanujan graphs. But for us, maybe we were more interested in what is the relation with free probability. And for us, maybe if we can say something about free probability from finite free probability or how this relates. And the fact that this approximates additive convolution, this was proved by Marcus and in our original paper with Daniel Perales. And actually, there was another proof in a note by Sheilaktenko and Gionet where they used concentration of measures. And actually, we included this proof just for the convenience of people, the audiences in our paper with Sam, or maybe we sketched the proof. So you can do this with concentration of measure. Okay, we do this combinatorially, and we also did this for the multiplicative convolution in a second paper with Jorge Garza. Good. So the main tool in this paper and this paper was what we call finite free cumulants. So by cumulants, basically, what do we want? So we want three properties. One is that we can recover the moments from the cumulants and vice versa. So this is a polynomial in the moments with leading coefficient the nth moment. Then we want homogeneity, which this comes from if you think of the multivariate version of multilinearity, right? This is exactly that, which is also true for moments. And the most important, of course, is that we can calculate our convolution by using these cumulants, okay, which we call additivity. Okay, so this is in probability if you do free independence or classical independence or any notions of independence. And for our operation, we had something exactly the same. A small typo, but okay, I can't. So again, we want this polynomial to be, so Kn to be able to be written in terms of the moments. Here I put this constant because this is just because this is more useful, because the calculations are more simple. Okay, but you can do the whole thing by multiplying this guy by the inverse of this coefficient, and everything will work. Second thing is you want homogeneity, and this should be x over lambda, but actually maybe you don't care about the formula. What you care is that basically if you multiply your roots by lambda, which is like multiplying by a constant, you want that this is homogeneous of degree n. And the last thing, of course, is the most important, is that we can calculate the finite free convolution by adding these cumulants. So this is what we want from the cumulants, and with the property we can say a lot. And we have these very precise formulas in terms, for example, if your polynomial is given in terms of the coefficients, you can recover the cumulants by this formula in terms of partitions and vice versa. Or you can also recover it from the moments. And maybe the formula that one should have in mind is this last one, which is saying the moments can be expressed in terms of the cumulants by some rational function. Okay, maybe it's 1 over d to the n and then some polynomial. And the nice thing about this formula is that we can get exactly what is the leading order. You see, the leading order will be the partitions, so this is on pair of partitions, such that the join is exactly the maximal partition on the reverse refined order. Okay, so and we have this restriction. So we want this, and we want that the number of blocks of this and this is exactly n plus 1. Okay, so one can prove, in principle, the number of blocks could be even 2n, but one can prove that given this restriction, this is impossible. And then you can go even further. What is the second 1 over n term? Okay, this is just the partitions such that the number of blocks is exactly n. Okay, and this gives the 1 over n term and so on. Okay.
The mu is the usual Mobius function.
Mobius function on the whole partitions.
So, like the crossing term should somehow vanish as the degree is going to infinity. Is that evident from this formula?
So what happens if you want to have like the moment cumulus non-crossing one? You need to modify because you see here you have partitions, right? So basically it cancels. This cancels because we are having partitions. So you need to go to this is one way to see this. Yes. So basically, yes, this is exactly what I will maybe mention. But okay, one thing is that this definition satisfies these three properties. Actually, the first two are very simple because this is just a polynomial in the homogeneous polynomial in our moments from this formula, and the last one follows from the other formula because we know how to calculate the coefficients. So it's not hard. Okay, and then in this theory you can ask what is the central limit theorem. I start doing convolutions, and what so this is you don't need cumulants to show this, but actually somehow you see that cumulants are exactly the analogs because in this case the cumulants are 0, 1, and 0, 0, 0, and this gives the Hermite polynomial. Okay, so very nice. Okay, and also we have the analogs of what we call free Poisson distributions, which are the polynomials which have finite free cumulants equal to lambda or lambda times d. Okay, and this gives the Laguerre polynomials. Good. Some small remark is that actually we have we can quantify the central limit theorem, and we have a Berry-Essen bound also in finite free probability. One other thing which we proved is actually that the only infinitely divisible measure in this or polynomial in this theory is Hermite. Okay. However, I must say that there is, as I mentioned, we can think about infinite divisibility, but in the large n limits. So somehow this makes sense, and there is this paper by Andrew Campbell on Apple polynomials, which is very interesting. Okay. Okay. And then the question is what happens in the large n limit. So one of the main results that is useful for us is that you can characterize, so you have a sequence of polynomials, and you want to ask what is the limit. So basically you make a measure which is concentrated in the roots, so the empirical root distribution, and then you ask if you can give a criteria to have convergence of this polynomial to some measure. And the thing is, well, this should be an R. So we have convergence in moments, so suppose this is compactly supported. And this is equivalent that your finite free cumulants have approximate your free cumulants. Okay? So normally, when we prove some theorem, maybe we show that the same cumulants approximate the same cumulants. Okay, this is obvious. But here is different cumulants that depends on D. Okay, and the proof is, as I mentioned, you look at the largest term, and then you see that the other ones go to 0. And basically you see that the moment cumulant formula, so the limit of, sorry, I messed up. Sorry, it's the other way. That this basically converges to the moment cumulant formula for each finite fixed n. Okay, so one example is, of course, we saw that the cumulants for the Hermite were 0, 1, 0, 0, 0. So in the limit, we get the distribution whose cumulants are 0, 1, 0, 0, 0, which is the semicircular. And similarly, for the Laguerre polynomials, we can see that the roots of the Laguerre polynomial, they approximate the Marchenko-Pastor distribution, which we also call the free Poisson distribution with parameter lambda. So this was done, but this gives a very simple proof and conceptual proof from this point of view. Okay, and then maybe one can ask maybe about this convergence, and this is direct from the definition of cumulants once we have this. Okay, maybe, and then one can ask how to prove this, and basically it's very similar, but we need a new formula, which is what is the finite free cumulants of the product. Okay, and we have this. You see, in the formula before about moments, somehow there was a lack of symmetry. Maybe I passed it too quickly, but it was everything. It was exactly this formula, but without this. And somehow you were summing over partitions, and there was some asymmetry, because this guy was related to this guy. Well, there was nothing related to this guy. It turns out that basically you put the cumulants and you get this very nice formula. Okay, and then again, how do you show this formula above in the limit? Yes?
So where does it have an R and a kappa in this formula? Is there a type?
Yes. That's an R. Thank you. Yes, sorry. Because I tried to change everything for R so that it was not confusing, but I did the opposite. Okay, sorry. Okay, this is an R. So this is the usual formula for cumulants for the free convolution, which is in terms of the Crera's complement. And one can show basically that this guy is like pi, and this is like the Crera's complement of pi. Okay, so we have very nice understanding on what's going on in terms of cumulants. And okay, then we can, this is how we prove this. Okay, and maybe this is very specific to this theory, but then you can say, what can you do with this? And actually, we were working with this because we were trying to solve the following problem using combinatorial tools, or at least give a new perspective of this theorem of Hoskins and Kablushko, which was conjectured by Steinerberger in relation to this paper by Shiraktenko and Tao, relating, because what Steinerberger notices is that this differential equation that they derive actually was known to hold for derivatives of random polynomials. So they give Hoskins and Kablushko gave an analytical proof, and we wanted to understand this. And what we proved was exactly that. Basically, we proved that if you take the derivatives of a polynomial, this converges to, so suppose that the roots of this polynomial converge weakly to some measure, then the derivatives converge to this free additive convolution or free additive powers. Okay, and the main trick was very nice observation. Okay, maybe some nice pictures. So intermezzo, nice pictures. Okay, so this is an example of, you start with 2 points, and you take the derivatives, and then you take the histogram of the roots. And we have this, for example, if you have half of the derivative, you have this arcsine law, and when n is large, you start looking as a semicircle. These are other pictures of Steinerberger. He didn't do derivatives, he did this differential equation. And even he can do this for random polynomials. And they show that you get a semicircle in this paper. They were not able to prove that what happens in the middle in this paper. But then Hoskin and Kablushko were able to do this. Okay, so and also we can prove that for the small regime, we can also prove this. Okay, good. So how do we prove this? Using finite free convolution or finite free multiplicative convolution, and the idea is very nice. So what is so the point is that we don't we look at free multiplicative convolution, but as having a multiplication with rank 1 matrix, rank n matrix. So basically what we're saying is, how do you cut corners? So in the talk of Vadim, he said that having corners is exactly having this free convolution. So how do you cut corners? Well, you multiply by 1, 1, 1, 1, 1, 0, 0, 0. So this is exactly this guy. So then you multiply and you realize exactly you get the derivative of polynomial times what you cannot avoid, which is the atom at 0. Okay? And then by using our theorem that this guy converges to the multiplicative convolution of the limits, so this is mu, and what is the limit of this? Well, it's just 2 atoms, 1 atom at 0 and 1 atom at 1. So basically, you are not seeing, okay, this is just a dilation. Okay, so you are not seeing actually free convolution. What you are seeing is actually free compression. So the conclusion of this, of all this, is that actually derivatives come basically from free compression. Okay, so good. So questions. Okay, so I will talk about another limit, and so this was a paper by Sakar Kavlushko, and this paper is very nice because he explained how what he calls unitary Hermite polynomial is related to various things, and he motivates the name. So I recommend to read this paper, but then he also proves that this guy, what is the limit of this guy? And if maybe you remember the talk of Marva, she talked about this free unitary Brownian motion. So what Kavlushko proved is that the marginals at time t converge to the marginals for the free Brownian unitary Brownian motion. Okay, so this is a polynomial that we call unitary Hermite polynomial, so explicit one. And okay, one thing I forgot to mention is that actually this comes from finite free probability as a central limit theorem for multiplicative convolution on the torus, so on the disk. Okay, and yes, and just a reminder about the free unitary normal distribution is just a guy who has this S transform, or these moments, or maybe for us, these cumulants. And what I want to mention is that actually, okay, how do you prove this? Actually, it's harder, okay? And this was an observation that by Jorge Garza, that this amounts to prove this other more combinatorial result, which was not obvious at all, which is what we proved in this paper by with Fuji and Ueda. We proved even more things, and we realized that other limit theorems similar to this one, in particular the case of unitary Poisson, also holds. But so this gave finite free cumulants gave this idea of how to prove this, and what I want to say is that sometimes it's not only using finite free cumulants, but you need new machinery and this new identity, which actually I never saw before. How much I'm on time?
You have like 7.
Okay, good. So then one can ask also, how are you approximating finite free convolution? Or how you are approximating a polynomial? So we know that the leading term is exactly this guy. So this is just a moment cumulant formula. And you can ask what is the 1 over n correction. And we found a formula. So you have a polynomial whose, so how to approximate a fixed polynomial? So our candidate was just fix the cumulants. So this is in particular the case for the Hermite. So we said that the Hermite polynomial has cumulants 1, 0, 1, 1, 1. How does it approximates semicircle, or even for the Poisson? So we had this scheme of approximation, and what we found is this nice formula if you like combinatorics, or this other nice formula if you like the Markov-Klein transform. Okay, so this is the Cauchy transform of the limiting distribution, and actually one can see that this is the Markov-Klein transform minus twice the Markov-Klein transform. Okay, so but okay, maybe you can say, okay, maybe this is very artificial. It's very artificial. Why would you ask maybe there is only very few examples where actually there is a polynomial whose free cumulants are exactly the free cumulants of the limit. Okay, so then we worked a little bit, and okay, maybe this is just two examples. The Hermite guy, so this guy gives the arcsine distribution and the Bernoulli distribution on minus 2, 2. And actually, this was known, and this was generalized by Dimitro and Edelman, that this coincides with the infinitesimal distribution of the GOE. So they proved that actually one can put a parameter, and the fact that these are negative and this is positive is just that the parameter beta, I think is 1 minus beta over beta or something like this. Okay, okay, good. But maybe more generally, you wants to know if you have some infinitesimal moments. So you have two polynomials, and I assume that they have infinitesimal distribution. That means I know what is the 1 over n correction of the moments, how to calculate the correction for the free additive convolution. And this is in terms of combinatorics, but actually we can also do this in terms of the infinitesimal distribution, in terms of this analytical tool, which is the Cauchy transform. And you see, this is the part that was related to the Markov transform, but in general, we can have a precise formula if you know how cumulants approximate. We have also a formula if you know exactly how moments approximate. Okay, so you can do anything. So what I want to say is that if you have in certain way your information about your 1 over n correction, we can calculate what is the correction for the finite free convolution. Either combinatorially or analytically. Okay, and maybe we can relate actually with the usual infinitesimal freeness, saying if you have infinitesimal convolution, so this is of the usual infinitesimal free convolution, and you have the subordination functions, then one can write exactly this as the infinitesimal distribution for the finite infinitesimal convolution plus this guy plus this term. Okay? So somehow this says that this is similar to infinitesimal free convolution modulo this term, and this is actually general, like the difference between having free cumulants and finite free cumulants. So somehow you can split. Okay. How much time do I have?
12 minutes.
Okay, I'm going quite fast. Good. So you can have some questions at the end. So I will finish by just two unexpected applications on finite free convolutions, since maybe the ones before were a little bit specific, but these two are very general, and I will try to explain a little bit. So what I showed you before is saying like how to calculate. So you have some polynomial, and you want to know if this converges. So I was trying to convince you that you can use finite free cumulants. But maybe you're not convinced, and you say, oh, actually, if I give you a polynomial, what I give you usually is just the coefficients. So the question is, can I give a criteria in terms of the coefficients? So for example, the Hermite, we know the coefficients very well. So you would like to know directly from the coefficients if this converges to something. So this was the question that we tried to solve. And so the coefficients are just normalized by t to the k. And we call the S transform, or the finite S transform, just to be the quotient of this guy with the next one. Okay, and what we were able to prove is that actually, so you see, if you have some atoms at 0, this guy is 0. So one should be careful about that. But other than that, it's just very simple. So the cumulants, sorry, a measure is converging to some probability measure mu. So for this, I mean the empirical measure of the polynomial D. If and only if this quotient of these coefficients converges to the S transform of Voiculescu at T. Okay? So what this is saying is actually that convergence of the coefficients is related to free probability, okay? Which is not obvious at all. And maybe I give a couple of examples. So for these Laguerre polynomials, so we know what is the coefficient, and we can directly calculate what is this finite S transform, and we get this formula, and this is just the S transform of the Marchev-Pastur. We can also do like Chebyshev polynomials, of course, and we get arc-sine distribution. We can get also, of course, we can recover the Hermite polynomials that they converge to the semicircular. Here you see a tilde. This is because for the symmetric case, one should be more careful because the coefficients are 0 on the outside, so we should just forget about the zeros, and this is exactly this definition. Okay, so this is this, and maybe I'll just talk a little bit about the proof of this. And actually, the proof of this uses this theorem. Of course, but if we want to use the S transform for multiplicative convolution, we should have another proof of this theorem because we proved this using multiplicative convolution. But actually, this is maybe a little bit embarrassing because one can prove this theorem directly from cumulants. And actually, the cumulants, so you see this polynomial is of degree D. No, this is of degree nj. So this means that you take derivatives d minus j. This is this symbol. So this is of degree j. And this is of degree d. And this is just derivating this guy and normalizing so that it is monic. And the relation between their cumulants is this guy. So very, very simple. And you see the definition of this is just that the cumulants are multiplied by some constant. So you do the calculation, and actually the proof that we had before maybe is very nice because it's intuitive what is going on, but this is like a two-line proof. Like cumulants are behaving very nice with respect to derivatives. And now we can use this result to prove the other thing. And actually the idea comes from this fact that the S transform, and I don't know if this was known. So the S transform of Voiculescu can be calculated by looking at the Cauchy transform at 0 of this guy. Okay, and then you can say, what is the Cauchy transform of 0? Maybe it doesn't make sense. But here we are positive, right? So the technical part of this paper is to show that at some point, and you need to know when, because if you wanted to show in the whole interval, to show that this is out of 0 for the interval that I mentioned. It is clear that it is out of 0 for large t, but if you want to prove it in full generality for exactly 1 minus the atom at 0 and 0, you need to prove for whole t here. You need to work a little bit more, but the idea is clear. So this is exactly the S transform. And actually, we discovered this identity because we wanted to prove, because we have this definition. And this is clear that this is, so on the other side, that the derivative at 0 is exactly what our definition. This is clear because when you take derivatives, the coefficients are shifted, and basically what you get is the coefficient E1 divided by E0, which is the inverse moment. So this is the inverse moment of, right? This is the integral of 1 over C. Right? So this observation is something that we learn from finite field probability. And more or less, this is my general message, is that finite field probability is giving new insights. Maybe some of them are very nice, maybe simple, but this gives new tools. Okay? And the other thing I wanted to talk about quickly, because Sam already explained, is this other result about entropic optimal transform that gives a description in terms of a maximizer of this quantity. And I will just mention maybe two key ingredients. One was this quadratic formula, and the fact that this goes to free convolution. That's why we know that we have this side. Okay, and the second part is, of course, the most technical part, and when it's to work is about what's the behavior of this guy by doing a large deviation principle on the permutation group. Okay, but what I want to say is that the starting point was exactly this observation of this, and that this goes to what we want. Okay, so let me just finish now, and maybe I can take